12.5, Part 1, Probability of Independent and Dependent Events. In Part 1, we'll be focusing on independent events. So the probability of an independent event is the probability of event A occurring and B occurring. So if the probability is of independent events, so the events happen independent of one another. In other words, B does not depend on A. B is not affected by A. So the probability of A and B happening are the probability of A times the probability of B. So in example 1, the probability of 2 independent events occurring. So it says a cereal company claims that 3 in every 125 people win a prize. What is the probability that you could not win twice in a row? So the probability of A and B is the probability of A times the probability of B. Now we have to be careful because A is not winning the prize on the first try, and B is not winning the prize on the second try. The two events are independent of one another. So not winning a prize on the first try is 1 minus 3 out of 25, because 3 out of 25 is winning the prize. So 1 minus 3 out of 25 is 22 out of 25. And the probability of not winning on the second time is the same because the probabilities are independent of one another. So probability of A is 22 out of 25 times the probability of B, which is also 22 out of 25. So 22 times 22 is 484. 25 times 25 is 625. And 484 out of 625 gives us 0.7744. Okay. In example 2, we're solving a probability equation, so we need to be really careful here. It says a manufacturer has found that 3 out of every 1,100 light bulbs are defective. How many light bulbs can you order before the probability that at least one light bulb is defective reaches 75%? So we're going to let N be the number of light bulbs you order. From the given information, we know that the probability that a bulb is not defective. Okay, so in other words, 3 out of every 1,100 are not defective. So the probability, 3 out of every 1,100 are defective, so that means that the remaining 1,097 out of 1,100 are not defective, which is approximately 0.997. Okay, so very, very high probability that the bulb is not defective. So we're going to use the probability and the fact that each bulb ordered represents an independent event to find the value of N. So the probability that at least one bulb is defective, we want to set at 0.75. Okay, so therefore we're going to say the probability that at least one bulb is defective is the complement of no bulbs being defective. Okay, so at least one bulb is defective is the same as the complement of no bulbs being defective, so it's also 0.75. So now if I substitute what I know, 1 minus, well, no bulbs being defective is the 0.997, so 0.997 raised to the nth power, because the n number of light bulbs, okay, is equal to 0.75. And we subtract 1 from both sides, so that's negative 0.997 to the nth power is equal to negative 0.25. Divide each side by negative 1, so we get 0.997 to the nth power is equal to 0.25. Now in order to solve this, I'm going to have to take the log of base 0.997 of both sides. So log of 0.997, base 0.997 of 0.997 to the nth on the left-hand side, and log base 0.997 of 0.25 on the right-hand side. So that gets my n by itself, but I've got log base 0.997 of 0.25. And since I'm going to assume that I don't have a graphing calculator, I'm going to use my change of base formula to say log of 0.25 over log of 0.997. And I can approximate that on any scientific calculator. And I get approximately, I think it's 461.4 or something like that, but we always need to round up when we're talking about things of this nature because we want it to reach 75%, so we can't round down. We need 462 bulbs to actually reach 75%.